welcome back. Today, we're diving into something that is, well, pretty mind-bending in the world of chemistry. Optical isomerism. We're about to see how certain molecules can pull off a really incredible trick with a beam of light.
Okay, so get this. Imagine you have two molecules. They're made of the exact same stuff, atom for atom, in the exact same amounts. So logically, they should be identical, right? Well, they're not. How is that even possible? That's the big mystery we're going to solve today.
The answer, and this is where it gets really cool, is a kind of hidden talent these molecules have. It's a property called optical activity, and it lets them literally grab a beam of light and give it a twist. This one little property is the key to everything.
So, let's unpack this light twisting trick. In this first part, we're going to unveil this hidden talent and figure out what's really going on.
Okay, here's the textbook definition. It says a compound has optical activity when it rotates polarized light. So, what does that mean? Well, think of regular light as vibrating in every direction at once, kind of chaotic. Polarized light is super organized. It's been filtered, so it only vibrates in one single flat plane. Now, when this neat, flat plane of light goes through one of these special molecules, it doesn't just pass through, it gets twisted. And this image here shows it beautifully. Imagine that polarized light as a flat ribbon shooting forward. Once it hits a solution with these molecules, boom, the ribbon comes out tilted. It's been spun either clockwise or anti-clockwise. The molecule has literally, physically rotated the light.
But why? What gives a molecule this incredible power? This isn't magic, right? It's chemistry. So there has to be something specific in its structure that makes this happen.
And that brings us right to our next section. We're going to find the source of this molecular magic. And it all comes down to something called the asymmetric carbon atom. All right, this is the key. A carbon atom, as you know, makes 4 bonds. Now, if every single one of those 4 bonds is connected to a different atom or a different group, that's it. That's an asymmetric carbon, and that little bit of imbalance is the secret sauce. Let's just build one real quick. You start with your carbon in the middle, then you attach 4 totally different things to it. What you've just created is a molecule that isn't symmetrical. The best way to think about it is, well, it's your hands. Your left hand and your right hand are mirror images of each other, but you can't lay one perfectly on top of the other. They're not the same. Molecules with an asymmetric carbon have this exact same handedness. And there you have it, this handedness, which chemists have a fancy word for. They call it chirality. That's what interacts with light. That's what gives the molecule its twisting power. If you don't have that asymmetric carbon, the light twisting trick just doesn't work. It's honestly that simple. Okay, so this whole idea of handedness brings us to a really logical next step. If a molecule can be right-handed, well, it's got to have a left-handed twin, right? A mirror image. And these two versions, these are our optical isomers. This chart lays it all out perfectly. You've got the right-handed molecule, which is called dextrorotatory, or D for short. It twists light clockwise to the right, and we label it with a plus sign. Then you have its mirror image, the left-handed one. That's levorotatory, or L for short, and it does the exact opposite. Twists light anti-clockwise and gets a minus sign. Okay, let's make sure these two terms stick. Dextrorotatory. Think dexterous, like being right-handed. It twists light to the right. And levorotatory, well, that's the other one. It twists light to the left. They are perfect mirror opposites in every way. All right, theory is one thing, but let's see this stuff in the real world. For our last section, we're going to look at a classic example that you'll find in biochemistry, a molecule called glyceraldehyde. So, meet glyceraldehyde. It's a pretty simple sugar, but it's the perfect poster child for this whole concept because, you guessed it, it has that all-important asymmetric carbon atom. And this is the aha moment right from our source material. When scientists actually put the D version of glyceraldehyde to the test, what did they find? It rotates polarized light to the right, just like the theory said it would. So D-glyceraldehyde is dextrorotatory. The name and the action, they line up perfectly. So here's how the whole story comes together. You've got 2 forms, D and L. They have the exact same molecular formula, but D-glyceraldehyde twists light to the right. It's dextrorotatory. And L-glyceraldehyde twists it to the left. It's levorotatory. And here's the most amazing part. They twist the light by the exact same degree, just in opposite directions. It's a perfect, beautiful symmetry of opposites. And that, right there, is the heart of what optical isomers are. They are perfect mirror images that you can't stack on top of each other, just like your hands.
and their opposite effect on light is a direct result of that mirrored structure.
So I want to leave you with one last kind of mind-blowing thought. Life itself, it has a preference. You know the amino acids that build all the proteins in your body? They're all left-handed. The sugars that give you energy, they're right-handed. Our entire biological system is built to work with one specific handedness. So, what do you think happens when our bodies run into the wrong one, maybe in our food or in a drug? That's when this cool little light-twisting trick stops being a neat party trick and becomes a matter of life and death.